All right. Hey, everybody. So I am, this is chapter three, part two. We're going to finish up today with energy. I needed to make a couple of announcements. So, number one, I'm going to try to do this without my headset today. So, you might have some background noise and stuff going on. Uh, Let me know if it's a problem and you didn't catch part of this. Number two, so the emails that I'm getting, I'm trying to respond to everybody as quick as possible. One thing I would like is for everybody to be a little more specific when you're asking a question. So, like an example, I got one that just said, I don't get it. I don't know. Sometimes I don't know what you're talking about. I mean, obviously, in that case, I wouldn't know what you're talking about, but try to be as specific as possible. If you're having a problem with a certain question, maybe take a picture of the question and send it to me and say, well, how do I do these calculations? Or if it's a concept thing like density or something like that, you can send me a question and say, hey, I can't figure out what to do with mass for density, or however. Try to be as specific as possible. That way, when I answer, I'm giving you the closest thing to what you need. Right? I need to be able to answer you in a way that's helpful. So if it sounds like I'm a little frustrated, it's probably because I am. But no worries. Just keep emailing me if you have problems. So we haven't really gotten into it yet. I think some people are still getting all their stuff in. But mastering chemistry, if you can't do a problem, send me a question. Send me a picture of which question you're having problems with, and I can maybe work an example, post it on Cougar View or YouTube for everyone to kind of see how the problems are worked. I try to do examples when I go through the lectures, but you're going to run into issues. So just send me an email. Let me know what part you're having problems with. I can do a video or I can respond to you directly and try to help you get through it. Okay? So that being said, everybody should have Mastering Chemistry in. If you haven't gotten it yet, but it's like on the way and should be here, go ahead and get the temporary access from the website. That'll allow you to complete assignments. So this Sunday, I'm going to start being stricter the um, with the grading. Okay, so I've been telling you that it's not a big deal or whatever. Like, I'm gonna give y'all time to get all your stuff in. So it says everything is due on the 6th, except for chapter 3, part 1. So you can still turn all of these in. I'll see that they're past due, but if you've communicated with me, emailed me that you've had problems getting your stuff in, and I know your situation, then I'll be less likely to take points off. Okay, so all of this needs to be done by this weekend. Chapter 3, Part 1, I'm going to use as a bonus, okay? Because there wasn't that many problems in there. I can't remember how many it was, but I'm essentially going to use that as a bonus and I'll add it on later. I'm going to add Chapter 3, Part 2 later on today, and then that will be due by, let's say, next Wednesday. That ought to give you plenty of time to do that and catch up with the previous assignments if you hadn't already. Okay? So that's the Master in Chemistry that kind of addresses emails. Um, okay, let's get into what we're doing today. So I started talking about temperature last time, but I want to back up after I talk about energy a little more. So energy is essentially just the ability to do work, okay? The ability to make things move or to store like energy. So when you think about energy, it is what it sounds like, right? It's like a force in the world that kind of there can be a kinetic energy and potential energy. Okay, so kinetic energy is the energy associated with moving things. So like a car, when it's driving down the road, if it hits something, it carries a lot of kinetic energy. So kinetic is those moving particles or energy associated with motion, um, swimming, water flowing over a dam, working out, and we'll do some more examples here later. Um, but the reason I bring up kinetic energy before I back up to temperature is it's important to remember that all things have energy. Okay, all matter has energy. and it's usually stored in the form of potential energy. Okay, this is energy like gasoline or batteries. Batteries is a good example. So when I have a battery, I have some molecules inside of it, and they hold a certain amount of potential energy that I can release by putting it into a remote control and completing that circuit. And then that energy is released and it starts moving, and then it becomes that kinetic energy. So there's like this play between these different energies, right? Something that's moving has kinetic energy. Once it stops, it holds on to this potential energy, and then I can use the different energies however I need to. So now temperature is a reading of how fast the molecules are moving within that system. Okay, so what does that mean? Let me do an illustration. Where's my iPad? Actually, I think there's one on the PowerPoint. Let me see if there's one on here. Yeah, here goes one. Okay, so kinetic energy, but this is talking about heat. Let me do the iPad. Imagine I have a glass of water here. Okay, so we said that. Remember, a glass of water is like a bunch of little H2O molecules in here, and they're all. Let me erase that and make that a little cuter. So they are all in here, and they're all moving around constantly. Okay, and that way they all have kinetic energy. Okay, all molecules have kinetic energy because they're essentially always moving. Um, how fast they move is directly proportional to the temperature, or is the temperature. Okay, so say this is very cold. Let's say it's like 30 degrees or 32 degrees, so right above freezing. These particles are moving very slow, so I'm going to put some little bitty arrows as small as I can. It kind of shows that these are moving, but they're moving very slow. Okay, so when I increase the temperature, say I say 100 degrees, and I got these same particles in there, these particles are moving very fast, and they're bouncing all over the place, hitting into each other. All right. So the temperature tells me essentially how fast these particles are moving inside of a system or glass of water or even air, right? A hot air is a bunch of molecules bouncing around way faster than cold air. And that's all temperature is, how fast those molecules are moving around in there. And it creates a kinetic energy. And then that energy that we read is expressed in terms of heat. Okay? And we think about heat being, just it's hot outside. But it's important to remember that everything has heat, essentially, because everything has energy. Um, how can I express this? So we said that, let me go back up here. So we said that all molecules have potential energy. We also said that mostly all molecules have kinetic energy. To some extent, they're always moving. So this energy that's always stored in a molecule, we express in terms of heat or calories or joules. Okay, they're all different forms of energy. Calories because we talk about it when it comes to food. If I eat a bunch of calories, I have to work out a lot to kind of burn those off. Um, it's not a coincidence that we talk about burning calories because they're associated with this heat metric that we're talking about. All right. So the heat is the energy associated with moving particles. We said that temperature is a measurement of that heat. So I use the easiest way to think about it is the energy is heat, and I measure that heat by temperature. Okay. Now, when we talk about solving heat problems, you're going to solve them and you're going to answer with these units, joules or calories. Okay, and they're both the same kind of forms of heat, but we use them differently in different problems. Okay, so that's how come you're going to need to know both of them. Just like we went back from Celsius to Kelvin, and you're going to use both of those going forward, you'll also use joules and calories going forward as units for energy or heat. Okay? Remember, heat and energy is essentially synonymous right now. You don't know any other forms of energy besides heat. Okay? And this is kind of an illustration when we were talking about the temperature. You see, the temperature is a gauge that reads the internal heat of the system. So I have a kind of slower system where the particles are kind of moving slowly around, but I heat up the atmosphere, and then after I heat it up, these particles are moving much faster. Okay, so it's important to remember that the heat is the energy I put in, and the temperature is the measurement that I get out. Okay, so I have to put heat in, but I measure it using temperature. Okay, so there's we said that there's the only two different types of units that you know so far for energy is going to be the calorie and the joule. So the conversions are pretty simple, but it's going to be important that you set it up correctly and that you're going the right way. So let's do calorie first. So 1 calorie is equal to 4.184 joules. Make sure y'all can see that. Okay. And let me make this a little cal. And so I made sure that this is a lowercase c because 1,000 calories is equal to 1 calorie, big C. Okay, this is an uppercase right there. So they'll try to trick you with that probably at some point. Little c and big C. So big C is like a kilocalorie, right? Kilo is 1,000. A kilocalorie is equal to 1 big C. Okay, big C calorie. All right. So that's just calorie to calorie. Let me do a calorie to joules. So we said 1 calorie equals 4. I can't write with this pen. 4.184 joules. Okay. Another way of writing this. Remember to set it up with your conversion factors. So what I'm going to do is 1 cal over 4.184 joules, or 4.184 joules over 1 cal. Okay, now I did both of these so that I could just pick one when I start solving a problem. This will be a good practice for you to do as well. Let's see. Let's say I want to figure out how many joules are in 50 calories. Okay, so what I want to do is I want to isolate the 50 cal because that's what they've given me. I want X to be on the right, X joules. And now I like to put my 50 over 1. That shouldn't be, let me see if that clears out better. Okay, 50. And then I'm going to choose one of these here to multiply by 50 over 1, 50 cal over 1 to get joules. So automatically I'm starting to think about which level my calorie and my joule needs to be on. So in order for the calorie to cancel out, I'm going to need my calorie to be on the bottom over here. And then I need my joule to be on top so that joule is also on the right. So joule on top, check. Calorie on bottom, check. Let's use that one. So 50 times 4.184 joules over 1 calorie will give me what, 20. Let me go to my calculator. What we say, 50 times 4.184. I'll clear all that. 50 times 4.184. 209.2. Okay? So 209, let's round it to 209. 209 joules equals 50 calories. 209 joules equals 50 little c calories. All right, so that's how you do that problem. Oh, I need to do temperature. I don't think I did a temperature conversion yet. So remember, we're going to have to do all of these conversions. You need to be familiar with it, do some practice. Just let me clear that and make it a little smaller. Equals 1.8. This is the formula for converting temperature. Okay, so TF is Fahrenheit and TC is Celsius. Okay, so let's say I'm trying to figure out the temperature outside, and I know that it's 80 degrees Fahrenheit. I want to figure out how much it is in Celsius. Okay, that TC is temperature in Celsius. TF is temperature Fahrenheit. Okay, so now what do? Let's first we want to move stuff around. So let me take this off. If I subtract 32 from both sides, that'll leave me with 48 equals 1.8 TC. Let's move this over here. 48 equals 1.8 TC. If I divide both sides by 1.8, it'll leave me with just the temperature in Celsius. So back to my calculator. 48 divided by 1.8 equals 26.7 roughly. So 26.7 degrees Celsius equals 80 degrees Fahrenheit. All right, that's how you do that one. If I'm going the opposite way, it's even easier. 1.8 TC plus 32. Let's say it's 30 degrees Celsius, and I want to figure out how much Fahrenheit. I can just plug it in. So 30 times 1.8 would be like, let me see, 54, and then plus 32 would equal 86 degrees Fahrenheit. So if you're going from Celsius to Fahrenheit, you just plug it in. It's pretty easy. If you're going from Fahrenheit to Celsius, you got to do a little bit more. Subtract 32 from both sides first, then divide by 1.8. Okay. There's also a formula like 9 over 5. If you're more familiar with that, by all means, you can use it. 9 over 5 is the same as 1.8, but instead they'll use a fraction. So just remember it's the same thing. All right, so where are we now? We talked about little c versus big C, okay? Now, a calorie is defined as the energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. Okay? So, you're going to see stuff like that going forward, specific heat and stuff like that, where it says it is defined by 1 gram water by 1 degree Celsius. Okay? So essentially what I like to do in those kind of, when I see that kind of wording is, so it says a calorie is the energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So there's a gram and there is a degree Celsius. Okay? So there's all of these units are in there, and it's going to be my job to figure out where to put these units. So by 1 degree Celsius, that makes it sound like it's grams over Celsius. Let's get to our problems, and then we'll start talking about how to set up those units. Okay, so here's some different energies that we use. And you see all this is in powers of 10, so this is actually a lot of energy up here. Energy radiated by the sun in 1 second is 10 to the 27 joules. Remember, we just said that 200 joules is 50 calories. Okay, so it is a lot of energy. Okay, so here goes a practice problem. You can go through and do set up the equations like we did for calories and joules and figure out how many calories, 150 joules of energy. Check your question, check your answer, and make sure you're doing it right. Okay, so we have a calorimeter. For those of you in lab, this is going to be the next section that we start getting into for labs. And a calorimeter is something that we can measure that heat. Remember, we talk about temperature, but temperature is more or less just an external reading. Okay, so in order to know the heat of a system, we need to know other things like the weight of it, right? Remember when I said I was just talking a second ago about how we set up these equations, and it said the energy needed to raise 1 gram of water by 1 degree Celsius. Okay, so temperature only takes into account the degrees Celsius. Calories and thus energy has to take into account how much of it there is. So that's how come we use a calorimeter. If I have a known measure, like a known amount of something in a system, and I can control how much the heat is let go into the atmosphere, then I can measure by temperature that heat or energy associated with this little system. So calorimeter allows us to do that, and that's what it does. It kind of traps everything in. It gives us we know exactly how much mass is in there, and then it has a thermometer hooked up to it, so I can tell exactly what the temperature change is. And then based on all of this information that I have, I can figure out how much energy is in that calorimeter or in this little space. Okay, and so this is how we kind of figure out how many calories foods have. We'll put your food in a calorimeter and then burn it, essentially, burn calories. And then we can figure out how much energy it is. Okay, how quickly it burns or how much the temperature rises when I burn it tells me how much energy is in there. So something with more calories will make the temperature go up higher. Okay, so the calorimeter, like I said, we'll do some experiments in lab and you'll get to kind of see how this works and do the calculations to figure out how much calories are in whatever we're going to burn, maybe bread or something, I don't know yet. Okay, so we talked about this, big C, little c. 1,000 calories is equal to 1 big C calorie. Okay, let me make sure we did, yeah, we talked about it, okay. So this is like the third time I've done this video. I've got a bunch of stuff going on in the house. All right, so it goes through, just kind of gives you some examples of how we look at energy in food, and it's important to remember this not just associated with food though. It's associated with everything. Wood, when I burn wood, it's releasing a bunch of energy. That's how come wood is a good fuel source. Gasoline's the same thing. It's not as great of a fuel source because it burns so violently. That was probably pretty loud. But that's how gas kind of works. It erupts violently and gives you a lot of energy in a short amount of time. Food, on the other hand, has energy stored in like little packets, so it releases slowly. Okay, that's the difference in food and gas or batteries or whatever, right? Food stores it in ways that we can break it down over time and use it how we need it. Okay, and then that's how come you have bad carbs, good carbs, bad calories, good calories, right? it's because of the way that those things break down. If I have to put a lot of energy into breaking down bad calories, then I'm wasting the energy that I'm getting from the calories, right? I want to have good, nutritious energies that I don't waste when I burn, right? Like I don't waste all my energy burning my energy. Does that make any sense? Anyway, um, so this is a cool little section, especially for those that are concerned with like physical therapy or health or nursing, stuff like that. These little, um, I mean, this is kind of how the body works, right? We process these foods. These are chemical reactions that are taking place, and that's why it's important for those in the healthcare industry to understand chemistry, um, because of all these little nuances to how molecules work, how energy is stored. It's mainly in molecules and thus chemicals. So some more study checks. Now, specific heat is the amount of heat that it takes to raise 1 gram of substance by exactly 1 degree Celsius. Okay, remember we said that calorie was um, specific to what? Water? Let me go back. Where did it say that? Ta, ta, ta. A calorie a calorie is defined as the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So it's important that we're talking about water, okay? And that's how come the calorimeter, we put water in, where's it at? We put water in the system. We put your little piece of bread in here. We burn it. However much the water raises, we can determine the calories. Now the specific heat is a little different. A specific heat is associated with everything individually. The specific heat of water is just one, coincidentally, because that's what we based the calorie on, was the specific heat of water. Okay? And you'll see that in science a lot. Like whatever the most popular, we might have talked about this already in terms of density. Remember, density is 1 gram per milliliter. 1 cc, 1 milliliter of water is equal to 1 gram. And that's kind of how we set up this little specific gravity scale. Well, the same thing is for specific heat. We set up the specific heat scale based on water. So the calorie is the energy it takes to raise 1 gram of water by 1 degree. The specific heat is the energy required to raise anything by 1 degree Celsius. 1 gram of anything by 1 degree Celsius. Okay? And so you'll do some more problems with that. We don't use specific heat that much in real life, but it is important to understand that um, everything has its own specific heat. Okay, and it works just like energy and the calories, in the way that calories does, except for it tells you um, how energy efficient that substance might be, right? If I have a high specific heat, meaning that it takes a lot of energy to raise 1 gram by 1 degree Celsius, that might be a heat resistant product, right? If I have a very low specific heat, meaning that I can raise the heat very easily, that might be a good conductor of heat. So like metal or some type of like a thermal radiation device, right? So that's how scientists and engineers use these terms to kind of create and make things in the world. So specific heat, like I said, remember it's essentially how much energy it takes to raise or lower the temperature of something. Okay? And so this is where I was talking about those units. Remember we said, actually we didn't say because I wanted to come back to it. But so specific heat is expressed in terms of calories. So specific heat, it'll be written as like SH, is expressed in terms of either joule over grams times degrees Celsius, or it can be expressed in calories over grams times degrees Celsius. Okay, so what does this mean? This is why we went over how to convert between joules and calories. Okay, so you're going to need to be able to go back and forth to both. And then if the problem gives you, so the problem will give you several of these units. Okay, so let's say the problem gives you, let me see if I got a practice one in the text. We'll do that. Temperature, energy, blah blah, energy values for food, specific heat, calculations. Okay, here goes one. Calculate the, where am I at? All right, during surgery or when a patient has suffered cardiac arrest or stroke, lowering the body temperature, reduce the amount of oxygen, blah, blah, blah. How many kilojoules are lost when the body temperature? Okay, so this is when I start writing down my stuff. Go here. I'm going to read the problem and kind of write it out as I read it. How many kilojoules? So it says X, I'm going to put X kilojoules. This should be a lowercase k. X kilojoules equals, how many kilojoules are lost when the body temperature of a surgery patient with a blood volume of 5,500 milliliters is cooled from 38.5 degrees Celsius to 33.2 degrees Celsius. Okay, so I'm going to go, I got an equation here. Specific heat equals heat. Let me write this down right here. So remember I said that joules is an expression of heat, calories is an expression of heat. So this equation, this on this page, these two equations are the same as what the text is giving you. Let me go back to the text. The text says heat over mass times delta T, but right here it says it could either be calories or joules. So you can use either calories or joules here, but it's important that you keep that unit the same when you go through and express it in your final answer. Okay? So specific heat is heat over mass times delta T. Delta T is just another little Greek symbol that we use for change. Let me show you here. Delta is equal to change. Okay? And when I say change, remember that is a difference. So a temperature has to change. Delta T is the final temperature, TF, minus the initial temperature, TI, gives me delta T. Okay? So the final temperature minus the initial temperature. And it's an absolute value, so if it's negative, just take off the negative. Okay? In this case, it should just be an absolute value. Well, let's test it and see. So I'm going back to reading my problem, and I'll finish writing this in. Let me go to a new page. So instead of, well, I guess I will use X. X kilojoules equals the heat over the mass times delta T. So let me go ahead and put my division line in there. Where's my problem at? I'm back here reading this. Okay. Blood volume 5,500 milliliters is cooled from 38.5 to 33.2. Okay. So I said delta T equals T final minus T initial. So the T final was 33.2. I'm just going to put the largest one first. 38.5 minus 33.2. All right. So that will give me, what is that, 5.3? So delta T equals 5.3 degrees Celsius. So let me plug that in there. 5.3 degrees Celsius. That's in parentheses. Okay. And then the other is the heat. Which is what we're trying to find. And then it says 5,500 milliliters of blood. So blood, I mean, I don't see where it says this anywhere. Oh yeah, it does. Assume specific heat. So let me show y'all this. I mean, I knew this, but I didn't know if they said it. Assume specific heat and density of blood are the same as water. So blood's mostly water. We're going to say that the specific heat and the density are both equal to water. So what does that mean? That means that, remember, 1 gram of water equals 1 milliliter. So then 5,500 milliliters will equal 5,500 grams. Okay? So now that's our mass. We had a volume and we said, well, what are we going to do with that? Remember, if I know the density, I can go from volume to mass. Okay? So that's going to take a little work. You're going to need to keep practicing with that. Where am I at? So 5,500, let me rewrite all this. X kilojoules, and actually I'm solving for heat. So you want to put the X kilojoules wherever. Remember, specific heat equals heat over mass times delta T. Okay? I'll put that in parentheses. Now they gave me a heat, which was X, or they asked me for the heat, which was X kilojoules. I figured out the mass was 5,500, and I figured out delta T was 5.3. Now it says assume the specific heat is equal to water, and we said specific heat of water is 1.00 joules per gram Celsius. Okay, so now I can, if that's just 1, then I can just carry this out. Okay, so multiply both sides by 5,500. That cancels out, and that becomes 5,500. And then multiply both sides by 5.3. So times 5.3. Let me do that here. 5.3 times 5,500 equals 29,150. So I'm going to rewrite all this so that it's nice and clear. Okay, 5,500 times 5.3 equals, what we say, 29,150 joules. Okay, so if that's in joules, then, and it wants to know how many kilojoules, remember a kilo is equal to 1,000. So 29 divided by 1,000 will be, 29,000 divided by 1,000 will be 29.2 kilojoules. Okay? So it can be a little tough. Oh, I did 1 calorie. Oh, I messed up. So I did right here for specific heat, I said 1 joule, but I actually did 1 calorie. Let me clear some of this off. And that's why I say it's important to get your units right. I messed up. So it's actually, it would be 1 calorie per gram Celsius. But since I'm solving the problem in joules, I need to make it joules. And that was my mistake. In joules, it's 4.184 joules. So then that times 5,500 times 5.3 would be just 29.2 times 4.184. 29.2 times 4.184 equals 122. If I go back and look at my problem, 120. 2 sig figs, so I rounded down to 120. All right. So remember, the specific heat of water is known, the density of water is known. Other problems will give you a specific heat and you'll plug it in place of this 4.184 over grams Celsius. Okay? All right, so next up we got changes of state. And they kind of jumped around a little bit. We've been talking about energy. We talked about the states of matter earlier. Remember, states of matter is solid, liquid, gas. Well, changes of state are terms that we use to tell you which, whether or not we're going from liquid to gas, from gas to solid, so on and so forth. And some of these you already know because we use them on a day-to-day basis. Ice melts, right? If I go from a solid to a liquid, I am melting. The Wicked Witch of the West. And then if I go from, let's see, evaporating liquid to gas, we call that vaporization. So evaporating is vaporization. Condensation, which we know is like when the gas turns back into liquid. So I have moisture in the air. It condenses on the side of a cold glass and makes liquid. So if I'm going from gas to liquid, that's condensation. Freezing, we freeze water to make ice. We melt ice to make water. That's more the way I think about going back and forth from there. Now, sublimation and deposition are ones that you're not going to see too often. That's going from a solid to a gas. The only like real life thing that I can think about that is sublimation and deposition is dry ice. I don't know if anybody's familiar with dry ice, but when dry ice melts, it doesn't turn into a water, it goes straight to a gas. So that's called sublimation. And then deposition would be when I made the dry ice to begin with. I had a bunch of gases, I compacted them in, I made them cold, and they went straight to solid. And they never turned into water before they became a solid. So that's deposition, and experiments we'll see this every now and then, but like I said, that one is pretty rare. Everything else you're pretty familiar with because we see on a daily basis. Condensation, vaporization, melting, freezing. All right. And it also talks about heat, so it's important to remember that everything has heat associated with it. Everything has energy associated with it. And if I lose heat, I'm getting colder. So freezing, the freezing process is heat being lost. The melting process is heat being gained. So keep thinking about heat in terms of energy. It's moved around from particle from system to system or molecule to molecule, whatever. But the way it moves has an impact on like how hot it is. Okay, so heat is energy, but it also, if you lose heat, things become colder. So it is exactly how you're thinking about it, but it's just important to remember that it's energy and it's transferred all the time. Okay, and so with each one of these little conversions, whether I'm going from solid to liquid or liquid to gas, whatever, there is a heat or like an energy barrier associated with it. It's essentially how much energy I need to put into ice to make it melt. how much energy I need to take out of water to make it freeze. Okay, and they have these different terms to kind of say that. The heat of fusion is the heat associated with melting. So from going from freezing to melting, or excuse me, from solid to liquid. If I'm going from liquid to solid, it's the freezing point. Let's see, whatever. Heat of vaporization. So that's the heat associated with moving from a liquid to a gas, evaporating. Let's see, what else? Do they talk about the heating and cooling curve? These are just graphical depictions of like how these dynamics work. It's not that important. You may see a couple. Notice that at the exact temperatures that ice melts and boils, there's a flat line here. That just means that while the water is converting from liquid to gas, the temperature stays the same. Okay? Any water over 100 degrees is going to be in gas form if the pressure and everything else is the same. Anything under 100 is going to be liquid. But right at 100, it's in this little in-between state where it's transitioning from liquid to gas. Okay, so that's all these little lines and these little curves are showing you here. Cooling curve has the same phenomenon going on. Okay, now this, I want to do one of these combining heat calculations. Okay, so let's try to do one of these and let's see how it goes. I'm also going to put some more YouTube videos up with this lecture video, so you can kind of go through if somebody else explains it better or talks about stuff that you didn't catch. Then you'll be able to use multiple resources to kind of acquire the knowledge that you need. But I'm also going to have math and chemistry problems. You got problems in your book that you can kind of work as practice or whatever. If you want me to kind of work out one of these practice problems that are in the book, send me an email and I can post a video probably pretty shortly after. All right, anyway, let's do one of these and just see how it goes. And y'all tell me, take a minute, do some practice yourself, and then let me know how everything is working out, okay? So, I'm reading this problem here at the top of page 85 in your text. Charles has increased his activity by doing more exercise. After a session of using weights, he has a sore arm. An ice bag is filled with 125 grams, so I'm going to write that in, of water. So it's ice though. I'll put ice, but in parentheses I'm going to put H2O because that tells me a couple things right off the bat. Number one, the density is 1 gram per 1 milliliter. So that means I also have 125 milliliters of water, or I will have 125 milliliters of water. Well, what else does that tell me? That tells me the specific heat is equal to 1 calorie per gram Celsius. Yeah, all right. So I put all that down. That's all from the first statement that I read. An ice bag is filled with 125 grams of ice at 0 degrees Celsius. So we said the ice is only ice at 0 degrees. So 0 degrees Celsius. I'm going to put that here. So let me start another little tab. 125 grams and then 0 degrees Celsius. How much heat in kilojoules? So it's going to ask for X amount of kilojoules. So that's a heat. I'm going to go ahead and start setting up my specific heat problem. in kilojoules, so I want to set it up 4.184 joules over 1 gram 1 degree Celsius, and that equals X, we'll just say joules for now, X joules over 125 for the mass, correct? And then the temperature change was up to 37 degrees. Okay, so that is a delta T of 37 degrees. But it made the zero made it easy to do in my head. Okay, so now I have looks like everything I need, I believe. 1 gram. So I need to look for the heat of fusion, right? Because I'm melting the ice, and so I can't believe it didn't give it to me right there. Yeah, that makes it a little more difficult. So it's 334 joules per gram. Okay, so that's how much is needed to melt exactly 1 gram of ice. All right, so let me see. So 1 gram of ice is equal to 334 joules. And this is 125 grams of ice. I think I'll just multiply it times 125 when I get done. Let's do it first. So remember, this is for 1 gram. 4.184 is for 1 gram. So when I multiply this out, let's see what happens. I'm going to my calculator real quick. 4.184 times 37 times 125. Answer. So that's 19,351. Let me write that in on my little pad here. So this one is 19,000. I'm solving right here. Actually, let me erase that and just write it. Bam. 19. What did I say? 351. 351 joules. Okay, so that's how many kilojoules are needed to raise the temperature from 0 to 37. But I also need to add energy for the energy it takes to go from ice to water. Now that was 334. Where's my pad? We said that was 334 for every gram. So that would need to be multiplied by 125 grams times 334 equals, put that in, 334 plus times 334 times 125. So 41,000 joules, 41,750 joules. What are y'all looking at? Okay. To go from ice to water. Okay. So let me explain what's happening here. We had a bunch of ice in the bag that we put on Buddy's arm. It was all at 0 degrees. Now remember, there's a bunch of energy associated with this transition. When we were looking at these heat curves, you see how it stays here at the boiling point for a long time? There's an energy shift going on there. And these are the heat of vaporization, heat of fusion, all of these different things that it was talking about. So when I go from freezing to melting, right, when I go from solid to liquid, there's number one, there's an energy change associated with turning from a solid to a liquid, but then there's also the energy change in the raising temperature. So that's how come you're combining both of these things. You found the energy it took to go from ice to water, and it was 41.7 kilojoules, or 41,000 joules. And then on this other page, we found that it took 19,000 joules to go from 0 to 37 when it's already melted. So if I add those together, 19.4 kilojoules from the 0 to 37, and then 41.7 kilojoules for I'll say solid to liquid. This is also called what? Heat of fusion. Yep, the heat of fusion. And so each one of these has their own name: heat of vaporization, but it's always it's going up, right? So heat of fusion, heat of vaporization. I add those two together and I get 161.1. Let's check our text and see if that's what they got. Roughly 61.2. Okay, so they did the same thing. They worked through it the same way. I'm going to put some more problems on Mastering Chemistry. Y'all check those out and see where you're getting hung up at. I know this is a little bit tougher stuff. So get a lot of practice in, because you're going to need to be able to work conversions easily. Especially, going forward, we're going to have a lot of this kind of stuff. So it's better for me if I know how you're doing. Usually, we're in person and I can see reactions on people's faces and stuff. Or when you ask me a question, I can look at your paper and say, well, oh, this is where you went wrong. This is where you went wrong. With this, I can't do all that, so I'm doing the best I can. Remember to be specific in your questions, and I'll try to help any way I can. Like I said, I'm going to post multiple videos on some of this stuff, so go through there and just kind of check and see how you're doing. Yeah, so you got till what I say, either Sunday or Wednesday. I hadn't decided yet. We'll see. I'll see how many problems I'll put on Mastering Chemistry, but these will take longer than the previous ones have. So get started on it and stay in touch. So I'll post the PowerPoint. Oh, excuse me. I'll post this video and the PowerPoints, and if I have any additional content, everything will be on Cougar View, so you should be able to just go in there and find it easily. All right. So that's it for today. I will see y'all either in lab or next week for lecture. Okay.